The equilibrium constant describes how far the reaction goes. It doesn't say anything about how fast it gets there. The reaction rate says how far it gets, how fast it gets to equilibrium. Every reaction has an activation energy or a barrier, an activation barrier that has to be overcome in order for the reactants to be converted into products. Usually this has to do with the breaking of bonds in the original compound. So you have to break the bonds before you can rearrange things and make new bonds, and that requires some energy. It's like getting ahead financially. In many respects, you need a little bit of money to get something started, right? You buy a bicycle and a trailer so you can go around the neighborhood and collect cans and recycle them and get money back. After you work at that for a while, you're going to make more money than you spent. But if you didn't have any way to get started, you wouldn't get anywhere. So it's this initial investment that most reactions have. It's called an activation energy. So we look at hydrogen and oxygen reacting to form water. Here's the energy of the reactants. Here's the energy of the products. Things like to go downhill. This is a spontaneous reaction. It's going to be exothermic and give off energy, but it has to go over a hump in the middle first. And this hump is because we have to break the existing bonds. That requires an input of energy. Once that's done, they will combine to form water molecules and give off more energy than was put in initially. But there's an investment that needs to be made. Startup costs. At a given temperature in general, the higher the activation energy, the slower the reaction rate. If you've got a really big hill to climb here, it's going to be a lot harder to get over. Fewer people are going to be able to get over the hill. If the hill is very low, more people are going to have that investment needed to get started in the business, and the reaction will go faster. So high activation energy, fewer reactant molecules can get over the barrier. They have to have enough energy. When we talked about collision theory, these guys have to collide with enough energy to break the existing bonds. The activation energy is the amount of energy that they need when they collide. The higher that is, the fewer successful collisions we're going to have, and the slower the reaction rate. Is that okay? You guys okay with that? Not that you not being okay with it is going to really change anything about chemistry, but I don't know. Can you speed up a slow reaction? Yes, you can. There's a couple things you can do. You can increase the concentration of the reactants. Increasing the concentration means more collisions per unit time. So more of those are likely to be successful. You'll get more successful collisions if you just plain have more collisions. You can increase the temperature. Increase the energy of the reactants. Then when they collide, you'll get more of those high energy collisions. The other thing you can do is use a catalyst. You can cut down the hill, take the top off of it, provide an alternate pathway. That's what a catalyst does. It provides an alternate reaction mechanism that lowers the activation energy. Thinking about pushing boulders off a cliff. Without a catalyst, we've got to push them up this hill. It's going to be slow going before they can fall down. With a catalyst, we've got a path around the top of that hill. A shortcut makes it easier. And so this is going to be much faster, right? Increasing the reaction rate is, by pushing harder, is equivalent to increasing the temperature. Well, we can make it go faster just by working much harder. Yeah, you can do that. Or we could take the easy way and just find an easier path. That's the equivalent of using a catalyst for a chemical reaction. So in this energy diagram, the effect of a catalyst is lowering this hump that we have to get over to get to the products. Catalysts are very, very important in your body. There are a lot, it's an understatement, there are a lot of chemical reactions occurring in your body right now as you're sitting here. And the rate of those reactions is very important. Some of those reactions have rates that are very, very slow under the conditions of body temperature and concentration. And you can't just go and heat up your body to make this one reaction go faster. One of the problems is that a lot of these molecules are heat sensitive, and you heat them up and you destroy them. So that's no good. You can't necessarily increase the concentration of the reactants. How can your body make this reaction go at a rate that is going to sustain life? By using a catalyst. And those catalysts are called enzymes. Enzymes are used to control the rates of reactions in your body. Here's an example of the hydrolysis of sucrose. Sucrose is a disaccharide. It's got two sugars bonded together. And your body needs to break that bond. It breaks it, and you get a glucose molecule and a fructose molecule. Well, under regular conditions, there's a high activation energy. It's going to be a slow rate of reaction. That's not going to work. But an enzyme catalyst, the enzyme sucrase, lowers the activation energy, causes the rate to go up. How does it do that? So here's an illustration of sucrase. It's got an active site, almost like a landing pad, where the sucrose comes in and it just nestles in, and it feels so good. And it's just in there. Nothing else is going to fit in there. Sucrose molecule comes in here and snuggles in, but when it does that, it gets stretched a little bit, and that weakens this bond that needs to be broken. When that bond is stretched and weakened, the activation energy is lowered, and the reaction rate occurs much faster. Once that bond is broken, the fructose and the glucose move off, and another sucrose molecule comes in. Very neat.